First up, my colleague and friend Dr. Reshmina William is here to talk about the movies. Dune Part 2 is an American epic science fiction film released earlier this year to critical acclaim. It's the second of a two-part adaptation of a 1965 novel, Dune, by Frank Herbert. Anyone who's watched it will recognise these clothes as stillsuits, moisture-harvesting suits for desert survival. So how realistic, how futuristic was Frank Herbert's thinking nearly 60 years ago? Well, Reshmina is a water expert at Isle and a wonderful sci-fi nerd, so who better to ask?
Hi everyone, my name is Dr. Reshmina William and I'm a project manager with the Isle Americas office. I'm also an unmitigated nerd, which is why I've been asked to talk to you all today about Dune and the science of stillsuits. Before I jump in today, I first want to acknowledge that I originally gave this presentation at Phoenix Fan Fusion earlier this year through the annual science programming offered through the nonprofit Real-Time STEAM. Sci-fi and fantasy is a wonderful on-road to STEM for the general public, so it's a great way for us as scientists and engineers to share why we love what we do. With that out of the way, I'll get off my soapbox and let's talk shop about water, and specifically about water reuse. So why reuse water? The point of the matter is that water is heavy. It's bad enough here on Earth where we have more than enough water to go around. It's just very badly distributed. That means that we have to spend a lot of energy to pump it from a river or a reservoir or out of the ground, and then treat it, and then send it off where it needs to go through thousands of miles of pipes. Imagine how much worse it would be if you needed to pay to launch all the water you needed into space. This is one of the reasons why folks like NASA are at the forefront of water reuse technologies. It's because those are the types of environments where it's especially needed. So when I talk about water reuse, I always like to talk about making it fit for purpose, which basically means making your source match your end use. There are many different sources that we can take reused water from. We can get it from rainwater. We can get it from gray water, so the water that's coming out of your shower or down your sink. We can get it from black water, the water that you get when you flush your toilet, or from stormwater, which basically means rainwater that's hit the ground and runoff, picking up any contaminants associated with that runoff into our storm sewers in our urban areas. And different source waters contain different contaminants that need to be removed. So that could be things like fecal pathogens or environmental pathogens, things that grow inside our distribution system, for example, like Legionella, or heavy metals like lead, nutrients like nitrogen and phosphorus, herbicides and pesticides, and so on and so forth. Then we need to consider our end use. You could be using water for irrigation, either for food or for non-food purposes. You could be using it to flush your toilet. You could be using it to wash your clothes. You could be using it in an HVAC system or as drinking water. And all of those different end uses have different levels of exposure and different exposure pathways to different types of contaminants. So, for example, if you're in a swimming pool or using water to water your lawn, you might be coming into physical contact with the water and be exposed to it through your skin. If you're in the shower, you might be drinking it, you might be breathing it in as an aerosol, or you might be drinking it or ingesting it with your food. Linking source and use together gives you your level and type of appropriate treatment, which could be physical or chemical or biological. All different types of treatment treat different types of contaminants and require different levels of energy and produce different byproducts. I've talked a lot about how water is used and reused here on Earth, but what about Dune? What about stillsuits? Well, we actually have a lot of the practical technologies that would make a stillsuit run, so I'll walk you through some of them. First things first, stillsuits need to be able to recycle the water from the human body, recycling of moisture from sweat, breath, urine, and feces. And we're already doing this on the International Space Station, which I'll get to in a couple of slides. So we have the technology to do that. Stillsuits need to have an in-unit portable treatment system and the ability to store the water that's treated. Now, the problem here isn't that we can't make the in-unit processes small enough. We actually have the technology to do that. The problem is, remember, water is heavy, and human beings produce a lot of it, between 1.5 quarts per day on a good day, and 1.5 quarts per hour if you're out there on a very hot day doing physical exercise. And all of that liquid needs to be stored and carried around. Water weighs about 1 kilogram per liter. So that's a lot of weight to be carrying around with you. The third challenge for stillsuits is maintaining a low level of humidity to allow physical functioning. Many of the treatment processes that I've talked about previously require physical evaporation. And so it's a tricky balancing act to maintain a suit that's waterproof, so you're not losing that water to the environment around you, but also allows the treatment processes to function in such a way that you won't kill the human being inside the suit via suffocation. However, the real challenge to creating a still suit in real life is figuring out how to create a self-contained source of power. If you look at the way that still suits are powered in the books or in the movies, they rely on the energy of the human body to treat water. So that's the kinetic energy you create by moving around, or your body heat. And despite the advances in treatment technology we've had over the years, we're not quite there yet. However, I do want to note that we're actually pretty close to achieving the impossible. This picture is taken from the International Space Station, and the instrument that this astronaut is holding up is called the Environmental Control and Life Support System, or ECLSS, because NASA loves its acronyms. And it actually captures the bulk of the water that's used in the ISS, and it's made up of 3 main components. The first is the water processor assembly. So this is the processor that's responsible for capturing moisture from the air that comes from our breath or sweat. And it's also responsible for the purification of wastewater. Secondly, we have the urine processor assembly, which distills urine on board and creates reusable water and brine as a waste product. And finally, we have the brine processor assembly, which takes that waste brine and extracts any remaining water from it. What this means is that when you put these 3 processors together, you have 98% water recovery, which is pretty incredible. It means that for every 100 gallons you send up to the ISS, you're actually reusing 98 of those gallons, which is pretty incredible. I wanted to end with a socioeconomic construct, which is the fact that water is undervalued until it isn't. So a common theme in economics is what we call the diamond water paradox. And this is an illustration of the difference between value and usefulness. We use diamonds for very few things, but they're clearly very expensive and very highly valued. Conversely, we use water in almost everything, but the cost of water in most places is so highly subsidized as to be almost negligible, a factor that has partially contributed to the US's crisis of failing water infrastructure. And while part of that discrepancy has to do with what's known as marginal value, in other words, the fact that a particular unit of water has less value the more of it there is available, it also has to do with the intrinsic cultural values of how we perceive water and its worth. Which raises an interesting question. On Arrakis, the desert planet, is the spice the most valuable commodity, or is it the water? With that, thank you for listening to this presentation. If you're interested in learning more about the work that Isle is doing related to water reuse, or you just want to geek out about stillsuits, feel free to shoot me an email. With that, Joe, back to you.
Thank you, Reshmina. Wasn't that brilliant? And I love the fact that science fiction is a route into science interests, even science careers, for lots of people. It makes perfect sense. I wanted to be a biologist in large part thanks to programs like Sir David Attenborough's Life on Earth and Blue Planet. So to learn that a totally different genre of programs is doing the same for other people, I think that's terrific.